I am investigating some specifications for the electron extraction chamber that I am building, specifically for the photon injection. As you can see here, I've got my screen up here. I've been asking ChatGPT a number of questions. My first one is just very simple. Can photons affect water? Photons absolutely can affect water, and they do in several important ways depending on the energy frequency of the light. Goes on to tell me about heating and infrared light, about how it warms water. Obviously, no light will warm water. And we get into excitation and molecular changes for visible and UV light. Chat says that they can excite electrons in the water molecules. That sounds familiar, doesn't it? This can slightly alter bonding behavior or energy states. This is basis of spectroscopy, studying how water absorbs light in different wavelengths. Stan Meyer talks a lot about this and the hydrogen fracturing technology, and this is kind of confirming it here as far as the actual science that's being applied to it. We're looking to excite the electrons. We're looking to alter the bonding of these. Breaking water molecules, high energy UV. Very high energy photons actually break apart water in a process called photodissociation. Then we have ionization. This is under extreme UV or X-rays. At even higher energies, photons can knock electrons completely off water molecules, can create ions, and that's like what we're doing. There's ongoing research on how light might influence hydrogen bonding networks, cluster structures in liquid water, coherent or resonant-like behaviors. How interesting. However, these effects are subtle and often debated. Low energy means heat, moderate energy means excitation, high energy means molecular breakup, and very high energy equals ionization. If you want, I can connect this directly to your work with resonance, da-da-da-da-da. And I said, please do. Alright, this is where things get interesting. What's really important is to separate what works physically from what just sounds right. So the real overlap, resonant does exist in water. Interesting, but it's at the terahertz frequencies, not kilohertz like what we're working with. Now, spectral absorption curve for water, wavelength in microns. Okay, absorption. Okay, obviously my LC system is in the kilohertz range, where water resonates at the terahertz frequencies. Obviously, a 5 or 10 kilohertz signal cannot directly resonate water, speaking with light energy. Bond breaking requirement, obviously it tells it needs a ton of energy to break that bond. That's obvious. You need UV range photons, high frequency, not low frequency electrical oscillation. Frequency alone doesn't do it unless energy per quantum is high enough. So what just happened when you apply kilohertz signals to water? I'm not sure if it's really getting what I'm trying here. I'm not applying kilohertz signals in LEDs, let's say. Dipole alignment. Interesting, yet that does the thing. Dielectric relaxation and ion movement. So it says where your work can become powerful, you're not resonating water. You're engineering energy delivery. Your system can step up voltage, shape waveforms, and control current versus voltage behavior. This affects efficiency of electrolysis, gas production rate, and heat versus reaction balance. The closest legitimate bridge concept, this is the one concept that sits between my work and photon physics. Field-induced effects. Strong electric fields can distort molecular orbits. We know this. We've done it. Can lower reaction barrier slightly, as seen in electrochemistry, plasma electrolysis, high field interfaces, but this field strength, not frequency magic. Voltage and field intensity matter far more than kilohertz tuning. That's true. We're talking about the voltage strength in between those two plates. That is most important. Bottom line, no fluff. Photons affect water only when their energy matches molecular transitions. Your system's real leverage is voltage, field strength, waveform control, energy efficiency. If you want to push this further, given your VSC transformer SRF work, the most promising directions are pulse shaping, high voltage, capacitive coupling, measuring phase shift, and looking for nonlinear impedance regions. This is where interesting behavior actually shows up. And I said, okay, if molecular bonds of H2O are weakened or broken, would ultraviolet light aid in the rejection of electrons from the atoms? Short answer, yes. Ultraviolet can help eject electrons or break bonds in water, but only if the photons have enough energy and the mechanism matters. It's not about helping along weak bonds so much as crossing specific energy thresholds. Let's break it down.
This is Stan's Revenge.
Two different processes, often mixed together. Bond breaking, which is photodissociation, which isn't what you're doing. We're actually relying on the voltage pressure to disassociate the molecules. We're relying on the photon energy to energize each atom more to a positive state, rejecting its electron even further. Let's see here. UV photons can break the OH bond. This creates neutral radicals, not free electrons. Electron ejection, which is photoionization. Higher energy photons can remove an electron entirely. This requires more energy than bond breaking. You get a positive ion and a free electron. That's what we're getting, a positive ion and a free electron. That's kind of what we're going for here. The energy thresholds matter a lot. So for bond breaking, you need near ultraviolet frequencies. For electron ejection, you need deep UV, vacuum UV. So not all UV is equal. Regular UV, like sunlight, UVA, UVB, usually does not ionize water efficiently. You need shorter wavelength, higher energy photons. Your question, if bonds are weakened, does UV help eject electrons? The nuanced answer, yes, but indirectly and conditionally. So yes, okay, it does. If the system is already electrically stressed, strong electric field, which it is, chemically active, ions present, which may be because we have voltage levels high enough in these successive tubes, or partially dissociated, which we kind of already do because of that high intensity voltage field. Then UV can lower the barrier for electron release, excites electrons to higher energy states, makes them easier to remove by electric fields, collisions, and secondary photons. Very interesting. So chat is basically telling me, yes, injecting UV light into the water as I'm splitting it apart, into the gas as it's split apart, can make electrons easier, more apt to be pulled from the gas or water. It'll increase ionization probability. Interesting. High field gaps right there. Where this becomes very real and useful. This does happen in advanced systems. Plasma plus UV environments. Photoelectrochemical cells, UV light, electrode bias, enhanced electron flow. Used in water splitting research. So it's like already there. High voltage systems, closer to your work. Strong electric field plus ultraviolet. Easier electron emission. More reactive species. Lower effective breakdown thresholds. So yeah, the idea is just to set up the conditions for the triggering effect. What Stanley Meyer always talks about. It's a triggering process. You're not creating all this energy, this thermonuclear explosion. You're in fact setting up conditions, like baking a cake. You can't just throw flour into an oven and expect a cake to come out. You have to set up the conditions to make it happen. So here we are. We're pulling apart the water molecule to begin with. We're taking it through additional chambers where we are exciting the molecules further. We're exciting the atoms further. So with photon injection and high intensity voltage fields, equal opposite polarity, we're literally pulling at those atoms even more, but the photons will be absorbed by the individual atoms, rejecting their electrons out of their shell further, allowing them to be picked up and plucked off through the electron extraction circuit. Important correction, this is where many go wrong. It's not weakened bond, low energy UV kicks out electron. It is electron ejection only happens if total energy, which is the photon plus the field plus environment, exceeds ionization threshold. Weakening helps, but does not replace the energy requirement. But we are just looking to weaken it. The voltage fields weaken it, the photons weaken it, and then we have particles bouncing around, which also weaken. So connecting directly to your VIC high voltage experiments, if you're working with high voltage, pulse circuits, low current, LC resonance, then adding UV in theory could increase free electron population, enhance ion mobility, promote radical formation, lower breakdown voltage in gaps, increase reaction rates at interfaces. But this becomes a photo-assisted electrochemical system, not a frequency resonance effect. Well, not an electrochemical system. This is a physical process. There's no chemical reaction happening, which I think ChatGPT still thinks there is, but there's no electrolyte. There's no chemical process that's happening. It's a physical voltage field physically pulling apart the atoms. So that's really cool. That it literally tells me that it could increase free electron population. So increasing the amount of free electrons even in the gas or the water bath. Enhance ion mobility, maybe allowing those ions to be moved to other places, or electrons being able to be pulled from them. Bottom line, UV can break water bonds, moderate energy. UV can eject electrons at high energy. If bonds are already stressed, UV makes electron removal more likely, but still must meet energy thresholds.
This is Stan's Revenge.
If you want to take this further, we can design a hybrid test setup combining high voltage pulse fields, controlled UV source, measurement of current gas production, I said, not all UV is equal. Regular UV, like sunlight, UVAB, usually does not ionize water efficiently. You need shorter wavelengths, higher energy photons. So I say, tell me what colors or wavelengths would be ideal. This is exactly where physics get very specific. The ideal wavelength depends on what you're trying to do. Break bonds, eject electrons, or assist reactions at an interface. Well, essentially I'm trying to eject electrons. We already broke the bonds per se, so we're trying to eject electrons. Those are different energy thresholds, so the color changes accordingly. So it shows here UVA versus UVAB and C, and then UVV, which is extremely short, very high energy wavelength. You may be able to do it with just low-end LEDs or laser diodes of some sort, but my theory is that you want the highest energy level possible, so the higher energy LEDs that you can get, the more chance you have of that process actually doing what it's supposed to. So for breaking water bonds, 240 nanometer and shorter. Practical range, 200 to 240. 185 nanometer mercury lamps is what it... Give me a real world example here. But for ejecting electrons, photoionization, we want 98 millimeters. Practical reality, this is a vacuum UV. These are impossible to find. Probably ridiculous amounts of money. Now, could maybe these be pulsed at a certain frequency that would more closely resemble the 98 nanometer frequency? Whatever that would be at. Can you flash these at that faster? Because he does talk about tuning in the frequency of light as well. So maybe you could use low frequency, low power LEDs, but you'd be able to pulse them in such a way to increase the energy level by tuning in to the frequency that would promote the ejection of the electrons. Now I wonder what frequency 98 nanometers would be. About 10 times order the magnitude of my operational. So if we do maybe a octave of that, multitudes lower than that. One important reality check. Even ideal wavelengths effects are surface level or low density. Bulk water remains mostly unchanged. That's okay. Strong effects require high photon flux or combination with electric fields. So if we combine the electric fields with photon energy, high photon flux energy, we may dislodge maybe one electron. But if we can dislodge just one electron and prevent just one molecule from reforming when we go to light the HHO gas on fire, that would equate to a tremendous amount of energy release just for that one atom that can't recreate itself. And that's the whole idea. You're setting up these conditions to allow a scenario to happen to where there's just not enough electrons to complete a molecular bond, and a hydrogen proton can't stabilize. And if it can't stabilize, it will just go into atomic decay and release untold amounts of energy. So just for giggles, I'm going to say design a hybrid system Goal: test whether UV exposure changes cell impedance, leakage, current draw, gas production rate, breakdown threshold, visible plasma glow, corona, pH, conductivity. This would help tell you if the UV is actually assisting the reaction rather than just adding heat or measurement noise. There are 2 UV modes. Good control wavelength, common germicidal wavelength, easy to source, mostly excites surfaces and contaminants, less chemically aggressive than 185. Mode B, 185, can generate ozone, can promote radical chemistry, more likely to alter breakdown conditions. Do not start with 90 UV. This is deep vacuum, ultraviolet, absorbed quickly by air, difficult to deliver through normal glass quartz, and not practical for open bench setup. Okay, that's good to go. Can't get it. UVC is hazardous, obviously. Hazardous to eyes, skin. And 254 nanometer exposure can injure the cornea. Ozone can also irritate and damage airways, so this needs sealed, interlocked, enclosed ventilation. Ozone handling. Yes, we're getting to more dangerous things here, so we need to be very keenly aware of what we are doing and the safety precautions of that. Use quartz, not ordinary glass, especially for deep UV. 0.5 millimeter to 5 millimeters. Interesting. Low conductivity water first, then controlled electrolyte trial. See, it still thinks I'm using an electrolyte. It just doesn't know what I'm doing. It knows, but it doesn't. Input voltage, 12 to 30. Pulse frequency, 120. Duty cycle, 5 to 50. HV output, 500 volt to 3 kilovolt pulsed. Current limit, hard limited below your target, ideally 100 to 500 milliamps during testing. Electrode gap, 1 to 3 millimeters. You want 4 simultaneous measurements. HV probe, oscilloscope channel 1, cell voltage, current shunt, current probe, channel 2, cell current, thermometer, flow meter, gas capture, gas output. What would count as a real result? Lower current, lower breakdown threshold, increased gas output, and change impedance, visible change. Okay, just blah blah, what to look for, etc., etc., etc. My recommended first build: a quartz window lamp, 500 to 1000 volt pulse DC, hard current limiting, oscilloscope voltage, gas collection by water displacement, which I've been doing. Then add 185 nanometer, or after the 254 baseline is repeatable. Bottom line: the most practical experiment is hybrid. Pulse high voltages water cell plus the UV. We're going to have to maybe buy some different LEDs. Might have to spend a few $100, maybe $1,000 or more on LEDs that I think will be appropriate for it. Also need to go through Stan's material again where he talks about the resonant chambers, the gas resonant chambers and photon injection. Just see if there's any additional little tidbits I can extract from that about what he was using and what would be appropriate. So, just want to put some thoughts out here. I can't believe this is 28 minutes already. I'm going to have to chop this up into a nice video. But this is where I'm at with the electron extraction, photon injection.
This is Stan's Revenge.